Yeah, that's fine.
So if you have that tiny kdump daemon started, does it overwrite or supersede the regular kdump?
No, I think it's sort of, there's some rough edges I haven't really seen too much about, but it basically, I think you just need to make a choice, so you have to decide which one to use.
Okay, so you choose it on your,
Yeah,
when you're
but
initially setting up.
yeah, for the some customers they're happy with the current kdump they don't need.
La la la. Can you hear me?
Ono to bude teraz dlho.
Hi, let's move to the next talk.
Our next speaker is Marko. Richard works at the ABRT team, but also on other projects, which it will be talking like right now about OpenCV and Tesseract, and its automated testing of graphical applications. So let's go.
So hello and welcome. My topic is this hot thing called graphical automated testing of graphical applications. And I will start with an outline, why I've started working on this, what's the motivation for this. I will talk about projects similar to mine, you probably know about as well. I will present my solution, my specifications of it, lessons I've learned producing this, current state of affairs, and the future improvements, and hopefully a demo. So let's start. So the motivation for starting this is validation testing of Fedora composes, which happens each compose, and is done manually currently. There is a lot of work for this, and a lot of people doing this. Some of them are probably here, from Fedora QA team. And this process is repeated multiple times for each release, and not only multiple times, but multiple times for each compose and each release phase, which is alpha, beta, and final. So, and the problem is that these matrices, test matrices that are evaluated for each compose are growing bigger and bigger because we are supporting more stuff. We have now products which differ in installation media and stuff. We support live media and net installation images, DVD images, of Pixie boots, for example, ARM, and now even the cloud images. So this is getting even harder and harder without automation is practically impossible to do by a bunch of people. So this is an example of a Testcase metrics, which is done for each release, each compose of Fedora. And you can see test cases that describe what should be done during the run. And brave people will do this. And this is a screenshot from Fedora project wiki. And the process looks like that when new compose is ready, for example, a test candidate for alpha release or a release candidate for final release, the new matrix is created with all these test cases like empty of these matrices. And people like voluntary start working on this and report results back to the wiki. So, and this is a collection of pages that are created for example, for a final testing of Fedora 21. So you can see there is installation testing, there is the matrices for desktop testing, for base, for cloud, and stuff. And this is repeated number of times because as of detailed tests, as some of the tests failed, we need new composes, then new compose is created, new matrix is created, and then the process starts over. So there are already projects that are trying to automate the testing of operating system installations and graphical applications at general. For the most, I don't know. These two represent, I don't know how to say that. I will start just describing what are these. So the OpenQA is the project developed by SUSE, and they are currently using it for automated testing of OpenSUSE factory releases, which are basically like nightly composes of Fedora, which we have now. It's now grown up to fully automated testing framework, which is composed of several components, and there's even a web UI and API for task management. It's grown quite bigger since I started looking at it. When I started working on my project, it was like 2 years ago, and OpenQA and its component was only one component, was the open how it's called? I can't remember. OS autoinst, yes. And there was very simple process done with this. And there were like, you have a segment of a screen that you save and you compute the hash of it. And then you look for a similar, when you repeat the test, you look for similar images on the screen. So, but this greatly improved over the last years, as I've found lately. So they basically reached the same problem as I've found, and now they are using OpenCV for vision, and Tesseract for OCR processing, optical character recognition, and the whole project is done in parallel. And this thing is quite actively used at SUSE. So they are now using a concept called needle. So you have a screen of an application, and you need to basically match templates on it or do some processing on it. So they call it needle, and it's description of the JSON markup with a area and type and method that you want to match on it. And with this is associated a template image, most often a PNG image that is matched against the screen. And then you can exclude some regions of screen or do an OCR processing on it. When this needle is matched, the current state of the evaluation is tagged with some text that you can use in your program to check whether you've reached some state or not. So a basic OpenQA test looks like this. It's basically parallel, which is interpreted. There's an assert screen call, which looks for a needle I've described before, which is called bootloader. It doesn't matter how it detects it. It's either OCR based or it matches a template. Then it sends a key, and then it waits for another needle to appear, which is a desktop needle. Well, this is a very simple test, but things get complicated when you get further. Okay, then there is a Sikuli project, which is kind of like university project style. It was started, I think, as an experiment of this user interface design group at MIT. It now contains the Sikuli script and Sikuli IDE components. Like what you get basically when you run Sikuli is an application. It's a full featured IDE for creating tests for clicking on stuff and for automating visual tasks, basically. So their stack is Java, Jython, and JRuby. They basically run all this stuff in Java, and your scripts are interpreted with either Jython or JRuby. So here's an example of how this looks like. This is actually a successor of this project called Sikuli X, which is building on the results of Sikuli.org, the two previous projects. I wasn't able to find a better screenshot of the original Sikuli, but the process is very simple. There's even a take screenshot or create region buttons that you can use to capture a current state of your screen. You're basically running an application, and you can click from this UI on select the region. You can drag a box over it, and you get it into your IDE, and you can use it in your script. So, and again, this is very, very simple, and probably it looks like it's doing some Skype calls. So, and now I would like to present my solution. It's called PLLM, but please don't ask about the name. It's meant as a flexible framework for testing applications. It's developed since Fedora 18, as I realized the need for this. And I started testing Anaconda with Vision and OCR and stuff. So, and now the goal is to automate this OCR processing and segment detection of the application. By basically using OpenCV to process images coming from a virtual machine over VNC and then pass them to Tesseract OCR for optical character recognition. So, architecture of this is now very similar to OpenQA, which is a server which is running a simple state machine. The process looks like that the server is started, it connects to your libvirt pool, create a virtual machine according to your XML that libvirt understands. Then it is started, its VNC is connected to the machine, and code interpretation is started. There is also another big component currently, which is a Vision and OCR pipeline, which is now running in a separate process to offload the computation even further and prevent some stuff I will talk about later. And a component which is a monitor for monitoring the process and interacting with stuff. So the most important thing of this is the Vision pipeline, which does a segmentation of the screen. I will show a result of one algorithm, which is maximal stable external regions. What it does is basically finds the connected regions that looks similar, and it's quite fast. It's quite good for detecting buttons. Then we have some other algorithms to run. That is the contour detection, which detects contours of text by eroding and diluting the image. I'll show examples of this later. And the K-means clustering for clustering color space into two clusters. Then we have another group of algorithms for Vision pipeline, which is OCR optimization. And these include simple stuff like thresholding, upscale, and filtering. For example, it was quite interesting to experiment with this, as you have a segment of an image, and you pass it to Tesseract directly, and you get garbage. And what happens when you upscale image 5 times? You get a perfect result. So that's it. I showed this. Then there is a contour segmenting algorithm, which works quite well for texts, basically, on the image. It also can find buttons and stuff. So this is the output of the algorithm visualized. And this is now then cut into separate segments and passed to on the pipeline, which takes care of the optimization for the OCR processing. And then there is a K-means example, which basically takes an image and does a color quantization on it, which produces a result of a 2-color image where the colors are clustered into 2 groups. Then there is a image optimization. What it does, it's basically simple. It takes an image and it's grayscale, it applies threshold, it tries its best to produce an image which is easily readable by Tesseract OCR. And there are some errors, like you can see there are challenges. When there's a background, then the thresholding sometimes doesn't work. You need to use adaptive thresholding or other algorithm, or retry with different parameters of the pipeline. Then there is a failed attempt of one storage device selected, which actually produced, you can probably see that, 31 swag device selected, which is not correct, obviously. So, then the lessons learned by developing this is that timing is hard. When you are executing a virtual machine and you are doing your processing of the results and interpreting your own code, you get a lot of timing issues or weird, hard to debug conditions that your program is stuck or the virtual machine is stuck or something is stuck. So this is now mostly resolved. No, next problem is that the vision is slow. The vision pipeline is now written in Python and is running on a separate process due to the timing issues that was causing some events to disappear. For example, when we were sending keys over VNC and their computation running, some keys disappeared. So the vision is now offloaded to another process, which is communicating with the main process. And when an image appears, it gets it and runs several algorithms on it and sends the results back to the main process. So parallelization is also quite hard. I've tried to make this vision pipeline configurable and parallelized, and I failed completely because I've tried to do this in like 3 or 4 days. It was way too hard. And the VNC causes troubles. I finally found what's this problem, which is a key handling. When you time your keys incorrectly, for example, you send a key press and then you release it too fast, for example, group won't register your keys, then there is another issue that sometimes key release is not registered. So what happens is that last key keeps repeating. That sucks. And there is another issue, and there is special keys. For example, when you want to send an underscore, that's quite hard. And there I even found a blog from Daniel Branch, which mentioned this, that more than you or I ever wanted to know about virtual keyboard handling, which is quite hard, and I'm glad they already solved this. And they've solved it by adding their own extensions to RFB protocol, which is used by VNC for passing keys. There are too many layers, basically, and too many conversions, and these conversions are lossy. So you have a key press, you over VNC, and you lose some information. And this is not good. So, but the solution exists, and is this extension to the RFD protocol, and they can basically send the whole key codes, not only keys, directed to the QEMU, and it can interpret the keys correctly. I will get to this as well during the demo. So, current state of it's a proof of concept, it works, it's not reliable, it passes installation quite often, but it's not reliable enough, like it's not 90% reliable. Well, maybe you will see a failure where it gets stuck somewhere or something like that. There are still key handling and timing issues, but most of them are now resolved. And the domain-specific language for writing the test is not yet finalized. There is also no GUI available, and documentation nearly non-existent, but I'm working hard on it. So, there's a future improvements I would like to add to this, and this is the faster and dynamic vision pipeline, which will allow us to process images more quickly, add stuff to it. For example, my idea is to have this project to get some people from the universities who are actually studying computer vision to work on this project and be able to add algorithms to the pipeline quite easily. Like, I want to add this. Okay, let's add it to the configuration, let's script something, and we can run it basically during the test. And the problem is that the parallelization would be really nice to this, and there is a screenshot from Gnu Radio Companion pipeline, which is really nicely done, and you can basically connect blocks, which are algorithms, and process data in the pipeline. And this is exactly what I'm doing currently. I get an image, I need to create the segments from it, so I can, and this would be an ideal result, and not only for this application, but for playing with computer vision by general, because computer vision is quite an experimental process until you studied it a lot and you can directly imagine what you need to apply on the screen to get desired result. So there is a lot of experimentation and tweaking and playing. For example, there's a lot of ways how to get from single image to the desired result. You can choose many paths, and such a designer for a vision pipeline would be really nice for OpenCV, and it's probably doable because their API is really nice. Then Optical trick recognition can also be, Tesseract can also use some training. This is basically using the basic data set which is provided with Tesseract and it's not trained specifically for desktop phones or the applications that it's trying to recognize. And then there is a collection of misspelled words, and I've already started working on it. You can use Levenstein distance and correct words that come from the OCR pipeline with small errors. Like, for example, what happens often is that there is a text partitioning, and when the block is not high enough, big enough, then the result is partitioning with Q instead of G at the end. So this can be easily corrected by Levenstein distance algorithm. And there is even a proof of concept implemented as well. So, Gnu Radio pipeline and demo time. Well, this will hopefully be more interesting. At first, I will show you a replay player I've put together tonight and try to play some of the attempts I did. So this is the actual result of the installation. What basically happens is when you start your process, it's saving each screen into its directory and running the processing on it, and then interacts depending on the results with the machine. So, and then there's some funny stuff going on. And at some point, when you try to delete your root, some weird things start happening, and there's even an AVC somewhere in between. So here it is. Let's try another one. This, for example. This is around where I actually found a bug with this tooling. And it's an attempt to configure partitioning, which fails at some point. Yeah, here. I can show you the image. There is one of the timing issues I've mentioned. The G starts repeating, and the mount point is not added with 5 gigs as it should be, but it ends up with 8 gigs. And then it tries to add more out, which gets error for, and then there are more errors and warnings, and then we have vision, we can correct the errors we make. That's the good thing about it. So it tries to correct, it tries to reset the partitions, and it clicks on reset selections, and it's still there. So it cannot correct because there's a bug. This is the first result I basically got with this. And I'll show you some more, like handling of special characters and underscores, which gone wrong. So again, we pass the partitioning, we get to the installation screen, fill the stuff. Then there's reboot, login. And then we start to terminal, and there was an echo command with underscores, which ended up like this. And my goal was to actually, as I'm part of the ABRT team, my goal was to install my favorite package, which is a will crash. What it does, it crashes. And then try to handle the error with ABRT. Oh, there were some network issues as well. But what actually happened is that I wasn't able to run, kill, or do these things because of the special characters. But hey, I'm still working on this. there's actually one which ends up in the GNOME ABRT, which was the ultimate goal of this. But there are no reports because of the underscores that are converted to slashes. And to show you how this actually works in more detail, I can get to some point and switch a type of the screen we use. And now we can, for example, see mouse, that's great. We can see the result of the maximal selected regions on the screens we actually process. I'm going the wrong way. So this is quite useful for debugging. As you can see which blocks and how good your algorithm performs visually. Then we have the contour segments algorithm, which can not only detect the enclosed regions of same color like buttons, but it's tuned to detect blocks of text, which is quite handy. For example, for a partitioning screen, where you have to click on the radio button, which is here. And there's even a problem here, which is the block is not detected correctly, but this is corrected by a further algorithm which merges the nearby segments into one and passes this through your pipeline. And then we have an inverted variation of this, which also detects these texts and stuff. So, and how does it look like? How does out of this look like? There's a directory structure created by this to make this better, bigger, with every screen which is stored, and you can basically look into the directory. It's called GQE, and check for the results of the algorithms. So, for example, let's go here. And here is the error I've mentioned, that these blocks are not connected. There is the segment merging algorithm, which can detect this and merge some blocks together. So this is now then passed into another algorithm which cuts the segments into parts and processes and does the optimization on this. We also does the optimization on the original image to get the overview of the text which is on the screen currently. So, okay, let's now go to an actual implementation. I want to show you how this code actually looks like. So, this is interpreted Python, which is running as a thread from the main process. And as you see, there's an expect call. There are basically two types of this. As I said, this DSL domain-specific language is not finalized. It's like big experimental how to do things. And actually, the OpenQA guys figured out that you need a state machine for interacting with applications. You can't do stuff the easy way, like wait and click and that, because bad things happen and you end up somewhere and you don't know where. So we have an expect call that tries to match these two templates. These are not processed by OCR pipeline due to speed and I don't know, results, whatever. And if it matches one of the templates, it calls the function which is specified at here. Then there is an expect text block, which tries to match the text displayed on the screen. So basically, when we get to the installation text is matched, and we jump to the Anaconda function, which does a lot of things actually. We have to do a mouse move for some reason, and then we try to click on continue. What this does, it actually waits until the screen changes and the pipeline returns results from the OCR, and then it looks for a segment that contains a click text continue on it. Then again, it waits for installation summary and goes to the partitioning screen, which is marked by installation destination. And it waits again, selects the I will configure partitioning screen, and then there is a specification for creating a partition. And how it works, we have a create layout function which calls this, which fills the data and clicks on the specific button. And then there is a detection if the stuff went okay. And if there's a click for details, like there was a warning, we detect this text, then we know we should reset the partitioning and start over. So, and this is how we basically pass the whole Anaconda. We pass the user's creation screen, set password to it. Password selection is also implemented with safety features, so-called. For example, if you provide a weak password, you need to detect that you need to click again on the done button. So it waits for new results of the pipeline, and if it does contain or provided a weak password, we know that we have to click on the done button another time. And if it contains do not match button, which happens due to the timing issues and the VNC problems, then we can try and replay what we've done, and basically correct the mismatched passwords. So this is it. And we wait for installation to finish. And if there's actually detection if we are running a live media or a normal DVD or a net installation, because on one occasion you have a quit button, on another occasion you have a reboot button. So when you have a quit button, you need to quit a button, and then you need to quit GNOME shell. So there's a special thing for that. So if we shall quit GNOME shell, we try to click on this, and then, well, and then there are other parts. We pass the GNOME initial setup and get to the help screen and stuff. So to actually run this, so I have these two things. There's a vision pipeline and a run script, which starts the whole process. It starts the libvirt domain. It creates its disk, everything connects to its VNC, and start interpreting our code. So if we open up image viewer, we can see a result, how it's actually interacting with the machine. And now this is actually quite a slow process, one would say, but to show you how it actually works, it's trying to match one of the expect texts I showed you. And when there is a new screen available, it's passed to the vision pipeline, which starts the tasks, which is currently on two tasks. One is OCR full, which does a full text recognition on the whole image to get the overview of what's on the screen. And there's a segmentation algorithm, which cuts the image into segments and does the OCR selected on each of the segments. And this is a sends back result of segment coordinates with their texts. So we are somewhere in here, and now it's basically interacting with a running virtual machine in here, and we will try to configure partitioning, install it, and basically test the installation. So I think I'm basically done here. There's some fun stuff I can probably show you, like garbled hello world and user Bob called BBO for some reason. So I think we could get to the questions and answers. Yes? I'm sorry. Can you repeat that?
The things that you're running,
Yes.
the script going
Yes.
through, does this text exist? Do you have any examples of that available publicly?
Yes, this is all published, and the code. There's only one example, basically, which is now installing the Fedora.
So that's in the same Git repository?
Yes, for now.
Okay, I wasn't looking for it now.
Yeah.
Thank you.
Okay, you're welcome. Yes, please.
Does it depend on the VNC and the virtual machines, or can I run it on the same machine that is under test?
The question was if it's dependent on the virtual machine and the implementation and the VNC, or if we can run it on the host machine against the host machine as well. So yes, it would be possible to run it against the host because you just need to run a VNC server like X11 VNC, but there's no support for this because this was mentioned to start to do automated process of the full virtual machine. But like yesterday, I've added the support for not recreating the machine, actually reconnecting to the running machine, so you don't have to wait for the whole process to finish to realize that you've made an error in your test, and you can actually start it from some point, for example, from GNOME shell, and it will catch up with the expect call and start executing these things. But adding support for different backends and even running against a host is possible. It's quite easy, I would say. Yes.
Is this publicly available, or will it be, or is this only?
Yes. There's a final slide, I think, and the link on GitHub is the publicly available project. I was running a short time trying to fix all the glitches that were appearing, so even this presentation is not where as it should be. But it's working. So in the upcoming days, I will add more examples and documentation, because this is basically usable now, as you can see. This is one of the most critical screens for some reason. More questions? Yes?
Actually, two questions. One is, I noticed that in the example code there is some stuff where you wait for the transaction and it accepts the DOM object as a parameter, and later on that stuff where they call methods on the DOM object.
Well,
is there an intention behind it, or is it
no. It's
you will clean up later?
yeah, I will clean this up later. I will do it like you don't have to pass the parameter to any of the functions because it's only one domain which actually it is running against.
And the second question is that do you plan to offer some functionality where you can, well, basically say maybe the OCR engine just look at that quadrant of
Yes.
screen or something like that just to speed things up a little? I mean, if you have
Yes.
something which takes really long and the
Well.
test takes a whole day or something, it might be nice if you could optimize this.
Yeah, this question was about optimization, and if it's possible to optimize the pipeline and actually tell it to look at a specific part of the screen, for example. And I was thinking about this. Now, the first optimization is that we are ignoring screens that are too similar to one another. For example, if there is a cursor blinking, we don't send subsequent images to pipeline because it doesn't make sense. And the second optimization I would like to do, it's slow now because it's running in Python and there's a global interpreter log causing all stuff, all sorts of problems with this. And I would like, as I said, to have this configurable and written, for example, in C++ for the speed because Vision, and then we can like process this much faster than this. Because now the processing, I think it's showing somewhere. No, there is no timing how long it does take. But for example, there are calls, and you can see how long it waits for some texts. And sometimes it depends on what the screen is on the text. If there are a lot of blocks, then you have to run a lot of Tesseract, basically. You either use Python API, which is suboptimal, or you fork, which is again not optimal. So
the whole legwork is happening in Python as well.
yes. Well, it's easier for prototyping, you know.
Yeah, sure.
No, and I was, sorry, another optimization I was thinking of, but I didn't want to cheat during the demo, was caching, basically. You have a screen, and you know that you already seen the screen and process this with this pipeline, so you can basically load results from disk and return it either way without further processing. Like disk memorization, yes.
Do you want people to start participating in the project?
Well, yes, I'm trying hard to actually make it usable and not glitch. Well, it works on my computer, so there are not even installation instructions on the GitHub page, but you can look at how stuff is implemented, and I will try hard to add all of these things.
Public background box or something?
No, that's a good idea, actually. So there's one more question, actually. Yeah. Yeah, but the prerequisite is to port the pipeline to C++, basically, and then you get the parallelization and acceleration of OpenCV stuff for free, basically. There is even OpenMP support for these things. What I was trying to do, to put each of these small jobs, like convert to grayscale, into separate small tasks that I could run in parallel, for example, but it's too hard to accomplish in short time without proper design. So, and we are out of time, and if anyone has a quick question. And the machine is installed, so even the demo is successful. Thank you.